Okay, so this is the calcitron. Idea is the calcitron is a linear neuron that learns using calcium-based plasticity. So we'll go through this slowly. But the general idea is that the way that neurons change their synaptic weights is that calcium enters the cell, calcium enters the synapse or the spine, and that's what creates these molecular processes that start plasticity. So just as a first approximation, the way that you get calcium into a spine. So we assume that there are two different mechanisms. One mechanism is the NMDA receptor. So the NMDA receptor is ligand gated, so it binds to glutamate. So you need a presynaptic neuron to release a neurotransmitter, and that binds to the NMDA receptor. NMDA receptor is also voltage gated, but we'll ignore that for a moment. We'll just sort of assume that the NMDA receptor is sensitive to local presynaptic inputs. That's kind of the focus. And then you have these voltage-gated calcium channels, which are voltage-gated, which means that they're sensitive to depolarization, which means that anything which depolarizes the neuron can potentially open up these voltage-gated calcium channels. So you can think, a postsynaptic spike, a backpropagating action potential, something like that, will give you calcium from the voltage-gated calcium channel. Now, when we think about a neuron, we can think about four different calcium sources or ways that you can get calcium. So one is, like we said, you can get local calcium from a presynaptic input that's synapsing on the neuron. So that's what we call CI local. My cursor keeps disappearing. And we're going all of these things. We're going to look at a real neuron, but we're also going to transfer it over to a point neuron, right? So if we have a point neuron and you're thinking about the local calcium, so this is sort of a perceptron-like neuron. So it outputs a threshold of the weighted sum of its inputs. So the local calcium, we associate each of these calcium sources with a coefficient. And those coefficients are Greek letters. So this one is alpha. So the idea is that however much presynaptic input you're getting at that particular synapse, so the input strength is xi, that's the strength of the input. And then there's some coefficient alpha, which determines how much calcium you get, which is a factor which is multiplied by the input strength. So that's what it is. That's the local calcium. And then you have what we call the heterosynaptic calcium, which people don't really talk about so much. But the idea here is that this is if you depolarize the dendrite, so you can imagine that even if you don't have a postsynaptic spike, but you have enough presynaptic input, so the whole dendrite becomes depolarized, and again you can open up these voltage-gated calcium channels. So that on the point neuron is associated with this coefficient beta. And that beta is going to be multiplied by the weighted sum of all of the inputs. Without the threshold, right? So whatever the total input is, irrespective of whether or not we have a spike, you can still potentially get some say global calcium to all the synapses through this heterosynaptic calcium.
So yeah,
yes.
Does W has certain rules, like proximity between different synapses? Or...
Okay, so in this model, there is no location because we wanted to keep it as simple as possible. In real life, location matters a lot for heterosynaptic plasticity, and so that's what one of our other papers is about with Menachem about the hierarchical heterosynaptic plasticity. But this is just a point neuron, so we're not worried about the location. There are no locations here. And the weights here we're going to assume for the moment are going to be all excitatory, and mostly just because this sort of calcium-based plasticity stuff is normally people talk about it with respect to excitatory synapses. It's less clear how plasticity works with inhibition. So this neuron actually has a bias term, which we don't show here, but the bias term we sort of think as an aggregate of all of the inhibition and the spike threshold. So the bias term will always be negative. So that's just You can think of the average aggregate inhibition. So these weights are usually only going to be positive. Yeah, so right. So all these Greek letters are a single scalar for the entire neuron. Now, in real life, that may not be true. So in real life, for example, you might have more NMDA receptors in this spine than in that spine. For the purposes of this model, we are not doing that. Okay, so that was the heterosynaptic plasticity, which is associated with beta. We have the calcium from the back propagating action potential, which is associated with the output of the neuron. So after we apply the threshold nonlinearity, the neuron gives us an output. In this case, the output is binary. Sometimes we might sometimes use the rate model, so the output won't be binary. It will be like a real number, but for now we'll assume that it's binary. And so that's associated with this coefficient gamma. So if you have a spike, then you get gamma amount of calcium, and that's broadcast to all of the synapses because it's a global signal. And then finally, we have an external supervising signal. So this is, I mean, for me, this is inspired a lot by Christine Greenberger's work on the entorhinal cortex to hippocampus circuit, where you have basically some sort of a circuit where you have a supervisory neuron or a supervisory signal that comes to the apical tuft of these pyramidal neurons, and that creates this large plateau, which in principle can send let's say depolarize the entire neuron, which causes calcium to come through these voltage gated calcium channels. So that's just this global external supervisory signal. And that's associated with this coefficient delta. So Z is the value of the supervising signal. So you're going to see a bit later that that sometimes you'll have a circuit with different supervisory signals with different strengths. But in this model, this coefficient is always the same. So we change the strength of the supervising signal, but the amount of calcium that you get as a factor of the supervisory signal is constant. It doesn't really make a difference, but that's how we do it. Okay, so those are the calcium sources. And now, how does calcium induce plasticity? So the basic model is this. This is the calcium control hypothesis, which initially comes from John Lisman, and was expanded by Chauvel and Graupner-Brunel in some of the more common mathematical formalisms, and also by myself and Lee in one of our other papers. The basic idea is that if you only have a little bit of calcium, so if you have less calcium than this threshold, which we call theta D, then nothing happens. If you have this sort of medium amount of calcium, so it's between theta D and theta P, so that's the depressive region. And then if you have a lot of calcium, that will potentiate the synapses. So this is the basic rule. To illustrate how this rule works, we have this stimulus that we like to use, which is basically we do a step of calcium, either a depressive step of calcium, which is between the depression and potentiation thresholds, or a potentiative level of calcium, which is above the potentiation threshold, and we turn that on for some time, and then we see what happens afterwards. So if you just use a sort of basic linear version of this rule, so effectively what you expect to happen is that for the duration of this calcium step, you'll just keep increasing the synapses, and then once you turn off this stimulation, this E stands for N, so you turn off the stimulation, it will just remain constant. Now, there's another way to do this. So you'll notice here that, for example, when you depress the synapse, so it goes below 0. So if you have a linear rule, that basically means that synapses can change weight, and also synapses can they can change sign and become arbitrarily small, arbitrarily negative, and they can also increase to an arbitrary value. In real life, that's not so plausible. So the sort of contemporary versions of this rule by Chauvel and Graupner-Brunel, and we're using the rule that Lee and myself developed, which I think is sort of the sort of most intuitive, straightforward way to characterize these rules. is what we call the FPLR, fixed point learning rate framework, where basically you decide on, okay, you say that there's a maximum and minimum value that the synapse can have. So here those maximum and minimum values are 1 and 0. And during the stimulus, instead of increasing forever or decreasing forever, you increase and decrease asymptotically towards these maximum and minimum fixed points. Now, for the purposes of the calcitron, this doesn't really matter that much. You can think about the linear rule or the asymptotic rule. It doesn't make such a difference. But one of the nice things about the asymptotic rule, it's just sort of sanity preserving, that you're not going to like turn an excitatory synapse into an inhibitory synapse, right? So you'll always be bounded by 0.
And what are the dotted lines?
Here,
Yes.
the dotted lines here are the fixed points. So this is
dotted trajectory.
the dashed lines. Yeah, so the dashed lines are the same as the solid lines. They just start at a different point. So we're just showing that, okay, so if you start at the highest value of the synapse at this potentiated fixed point, so this is what the trajectory will look like. And if you start sort of at a middle value, this is what the trajectory will look like. So it's the same equation, but just to illustrate that if you start at different starting points, so this is what the dynamics will look like. Okay, so this is the plasticity rule. And now the game is going to be, the idea of the calcitron is that we want to be able to implement different learning and plasticity rules, and there are going to be a lot of learning rules that we do. So that's the idea. We're going to implement these different learning rules just by sort of deciding on what these coefficients are going to be, and by, let's say, designing the circuit and designing the stimuli in a smart way so that we can get different kinds of plasticity.
So the injection time of the calcium is the same in all those schemes, but you change just the time constant of the decay, right?
Where here you're saying?
No, in all the simulations we will see.
No, so okay, so
okay,
no, so I should say, so in the simulations that we'll do, I think it'll be easier if I just show you. So it's not there isn't really any time in the sense that it's sort of like if you think about training a perceptron, right? Each step in the training of a perceptron is you present an input pattern to the neuron, and the neuron produces a response. And then you change the weights according to a learning rate. So it's the same thing here, right? So each step you change the response according to the learning rate. So it's discrete in that sense, but you still have this asymptotic effect, because you imagine that you potentiate and potentiate and potentiate just like step after step. So it will have that dynamics that it will increase asymptotically as opposed to linearly. Right. So it's not actually a prolonged step. It's discrete small steps. So the first thing that we want to illustrate is the basic Hebbian learning. This isn't really a learning so much because there's no real task here. But what we're going to do is we're just going to randomly present a bunch of binary patterns to this neuron. And depending on, say, how many inputs are in the pattern, just randomly, sometimes the neuron will spike and sometimes not spike. So there's sort of the standard basic version of the Hebb rule, which is fire together, wire together, which means if you have a presynaptic input and a postsynaptic spike, so that synapse which fired at the same time as a postsynaptic spike, that synapse will potentiate. So in this version, there's no depression. So how do we implement this using the calcitron? So we set the coefficients of alpha, which is the coefficient for the presynaptic calcium, and gamma, which is the coefficient for the postsynaptic calcium, such that when you only have a presynaptic spike, it's below the depression threshold, so you don't get anything. When you only have a postsynaptic spike, it's also below the depression threshold, so you don't get anything. But when you have both of them together, so it will induce potentiation at presynaptic synapses that have the presynaptic calcium, right? So this would be the situation for the synapses that were active at the time of the postsynaptic spike, whereas for other synapses, this will be the situation because they only have the calcium from the postsynaptic spike. So the way that we illustrate what's happening in the calcitron is we have all these plots here. I'll go through them one by one. So the first plot here is the input. So along the x-axis is time, and at each time step we present one of these binary patterns to the neuron. So the binary patterns, you can see it's here. So each of these squares, if you go vertically, is different synapse. So here there are only, let's say, 10 synapses, right? So this is the pattern at time step 1. That's the pattern at time step 2, and so forth. Now at each time step, there's also an output, which is the voltage. And if the voltage is above the spike threshold, so the spike threshold is denoted by this dotted line here. So if the voltage is above this threshold, then you'll have a spike, and the spike is denoted by a red circle as opposed to a black circle. Okay, with me so far? So here, right, these spikes are this just happens randomly because these happen to be like large patterns. So you just happen to have spikes. And so now what we can do is we can look at the calcium level at each synapse. And the calcium level is just a sum, in this case, is just a sum of the calcium from the presynaptic calcium and the postsynaptic calcium from the backpropagating action potential. So you can see, let's say we look at this first pattern here. So some of these squares are lighter and some of them are darker. Why are some of them darker? So the ones that are darker correspond to the synapses that had input, right? So the black synapses here are the ones that have more calcium here. And now so we have these plots here, which indicate the plasticity. So this is just red means potentiation and blue means depression and white means nothing. So in this case, with regular Hebbian learning, these synapses that have more calcium because they were active and because you also had a spike, so those are going to be potentiated, and the other synapses, nothing happens to them. So that's what happens on an iteration where you do have a postsynaptic spike. And you can see overall that because there's no depression here, just over time, all the synapses will get stronger, right? So more red means stronger synapses. So all the synapses get stronger. This is not surprising. And also realize with Hebbian learning, if you don't have depression, you have a feedback loop, a positive feedback loop. Because you can imagine if you potentiate a synapse, so the next time that synapse is active, it contributes more voltage. And so it makes it more likely to have a postsynaptic spike. So with regular Hebbian learning, you have a positive feedback loop, and you very quickly kind of potentiate all of these synapses. Now I should just say, if you look at situations where the neuron doesn't spike, and again, this is just randomly, so this black situation corresponds to this yellow vertical line here, and you see that you have that when you don't have a postsynaptic spike, so nothing potentiates, right? So you need both the presynaptic and postsynaptic calcium.
Really?
Yes.
It seems in the calcium total that when I'm comparing it to the other diagrams, it seems that there is only depression in the weights, right? Because the amount of calcium is low, no?
Here?
Yes. It's like kind of the same, no?
What is kind of the same?
The color of the calcium.
So I mean, it's hard to see here, but there's like a darker yellow here, and this is orange, right? This is bright yellow. I may not have, I may have an issue with the normalization. These may not all be the same. So just for now, look at each of these independently. I'll fix that. Yeah, I think so. Okay, but anyway, this is the standard fire together, wire together case. Now, there's another kind of Hebbian plasticity, which is fire together, wire together, and out of sync, lose your link. Sorry. So what that means is that if I have a presynaptic input and there's no postsynaptic spike, so I want to depress that synapse. So that's what you have in this situation where you only have a presynaptic input. It's above the depression threshold, you depress the synapse. Similarly, if you only have a postsynaptic spike and you have a synapse which was not active at the time of that postsynaptic spike, so we also depress that synapse. But again, if they both co-occur at the same time, so you have both together, you have potentiation. So that is this situation here. And because I explained everything else, but the idea is that you have these bright yellow regions, which are where nothing happens. So bright yellow basically corresponds to you neither have a postsynaptic spike or a presynaptic input. So that's the bright yellow. And then you have the orange. The orange is where you only have presynaptic input, or you only have postsynaptic spike. So that will cause depression if you look at this depression potentiation plot. And you have these dark regions where you have both at the same time. So that will cause potentiation. And this learning rule will give you a sort of more balanced more balanced synaptic weights at the end. So you'll have, because you have both depression and potentiation, you also look at the spiking at the end, and it's more balanced. So like here, with if you just have fire together, wire together, you know, everything just starts spiking all the time. Here it's more balanced. Now yeah.
So here you also have some calcium from other synapses, right?
Heterosynaptic calcium. Okay, so I should say that the way that we do this is that we choose which calcium sources we want to focus on for each particular learning rule, and then we set the other ones to 0. Right. So here there's no heterosynaptic calcium because we set beta to 0. That's how it works. So in principle, yes, you can imagine a learning. I mean, we'll show a learning rule later with heterosynaptic calcium, but this one does not use that because we're just doing like basic Heb and anti-Heb.
Okay, so A is end, right?
Yeah.
And B is end and SOAR for depressions.
Like
End is potentiation and SOAR is depression, right?
you can think of it like that, I guess, if you want. Yeah.
Okay.
It's a three ternary. Yeah, it's a three option.
Yeah.
Without
Okay. So there's also anti-Heb. So what's anti-Heb? Anti-Heb is the opposite of Heb. So you have fire together, lose your link. So this one, where is my cursor? This one is the opposite of this one. So here, if you only have presynaptic calcium or only have postsynaptic calcium, you get nothing. But if you have both, then you depress. So we see that here you only have depression and all the synaptic weights. Eventually you let it run, the synaptic weights get weaker, voltage goes down, you have less spiking. And now you have the penalization version of anti-Heb, which is fire together, lose your link, and out of sync wire together. Now if you it doesn't rhyme, so it can't be true. So in order to implement this, you have to reverse the plasticity thresholds. And this just has to do with the logic of how it works. So right, if you fire together, when you fire together, you always have more calcium than we have each of them individually. So that means in order to get this case to depress, but the individual cases to potentiate, you have to switch the threshold. So who says that we can switch the threshold? So it turns out that in Purkinje cells, people think that the threshold are reversed. Now, why do people think that the thresholds are reversed in Purkinje cells? Because they observe this kind of plasticity, right? So that's right. So in a sense, this is a way of getting some intuition about what has to be true in order for particular plasticity results to occur. And so this, like I said, this is the reverse case of this case of the fire together, wire together, out of sync, lose your link. So again, you have both potentiation and depression, but now they happen at the opposite time. And so again, you sort of have a more balanced synaptic weights, more balanced synaptic output. So that's Heb and anti-Heb. Any questions about that? No.
Try
Yeah.
to see the connection between the weights during time between the B and D.
B and D. Sorry, what's the question?
Looking at the weights and the correlation between them.
Yes. So right. So you'll see that this should sort of be the reverse of this, and it kind of is. It's a little bit subtle, both because of the asymptotic nature of the FPLR rule and because there might be different learning rates for, well, here the learning rates are the same for potentiation and depression, but also because of the feedback loops. Right. So I don't want to get into it, but that observation was generally correct, that the reverse things happen, but it's not necessarily 100% correct.
Yeah, that's what
Yeah.
I'm sure to understand what you actually do.
Yeah.
Is there a real neuron model here? Or is it the abstract? When you say I'm activating synapses and I'm activating you.
It's this neuron. It's this neuron here. It's a point neuron.
It's a point neuron. I'm asking
Yeah.
you, but it's a point neuron, but
Yeah.
this neuron is an integrated prior neuron? Is it a rich simulated neuron? Or is it an abstract neuron?
It's an abstract neuron. It's a perceptron, basically. Yeah.
It's not a neuron simulated.
Right. Right. Because the idea is we want to take away all that complexity of let's say the time dependence and all that, and really just look at what kind of learning rules we can implement in sort of the simplest sense.
But so what you're saying is that you can decide a priori on the threshold level, and then for this presynaptic thing to do this kind of amount of calcium, the postsynaptic will do this another amount of calcium. And you can play with the rules to decide a priori which one of them will implement STDP-like rule or anti-Hebbian-like rule, and that's what we actually showed us. If you can play with this threshold issues and contribution of calcium for each of these type of inputs, and get all these possibilities in principle.
Right. So that is the game. Now, I should say specifically with respect to STDP, we actually can't implement in this model just because there's no like real temporal aspect here.
Okay, but
Hebbian we can do. So that is Hebbian. And so I presented this at Ein Gedi also, but if you just think about theoretically what are the kinds of plasticity rules that you can get just from presynaptic and postsynaptic calcium, and you work out all of the cases, it turns out that there are 14 different cases. And this is just with the normal plasticity threshold, so depression is below potentiation. So people don't normally think like this, right? People think maybe Hebbian, anti-Hebbian, but people don't think that, let's say, if I only have presynaptic calcium or if I have both, then I get potentiation, but if I have a postsynaptic spike, then I get nothing. So this is actually, we have this with like frequency dependent plasticity, right? So this case basically says that whenever I have presynaptic input, I potentiate. Or you can have a case like this, right, where whenever you only have presynaptic input, you depress, but if you have a postsynaptic spike, you basically potentiate all of the synapses, irrespective of whether there's presynaptic input there, right? So there are all these different plasticity rules that you can have that are consistent with the calcium control hypothesis. No, I should say because Chaim Sempolinsky asked me at Ein Gedi, are there any rules that you can't implement with calcium? So the answer to that, even here, is yes, there are. Because if you just think about theoretically, what are the possible cases, right? So you have presynaptic only, postsynaptic only, and both, and then you have three situations or three different types of plasticity that you can have. So you can have nothing happens, depression happens, or potentiation happens. So it's 3 times 3 times 3. So in principle, there are 27 possible situation plasticity combinations, but the way that the calcium control hypothesis works, it constrains you to 14 of them. And the reason why you have that constraint is, again, because when you have both the presynaptic and the postsynaptic calcium, it always has to be more, right? It always has to be the sum of each one individually. So that actually imposes a constraint on the plasticity rules that are possible to implement.
But if you
both is dependent on each.
כאילו הסייג שלך הוא נכון במקרה הזה של הפשן, שאתה הופך אותם, שזה אומר שכן יש איזושהי אינטואיציה שלפני מפתוחה א'. רציתי לשאול לגבי שתי שאלות. א', כאילו עד כמה טייט הפרמטרים צריכים להיות, והאם יש יחס ביניהם שאתה יודע, מבחינה ביולוגית. כלומר, עד כמה אתה צריך to find tune את הפרמטרס כדי לקבל את זה, לעומת איזשהו דיפרנס שאולי טריוויאלי, ואז האם חלק מהרוץ האלה הם לא ריאליסטיים, כי תמיד, אתה יודע, ביחס כזה
Okay, so in terms of the question of the jitter, so basically the way that you create these rules is that so you think in terms of constraints, basically. So in order to get this particular rule, I know that alpha has to be less than like theta d or something like that, right? So you basically you come up with a set of like 5 constraints or whatever, depending on how hard the problem is. And any set of coefficients that satisfy those constraints, you can use and get the rule that you want to. So normally it's not like super tight, but sometimes it will be like just because if you have a more complicated rule where you need more things to be true, so you impose more constraints, so it will be more constrained. So with respect to what
It's a very good point, because to develop intuition, because there are different parameters, and you say maybe 5 constraints, or I don't know how many constraints. If there is some kind of a rule that you can really say, okay, if I take alpha above and this below, and that all this is what will happen. If you can define a systematic rule that I can then understand, if I want this to happen, then I need this to be above and so forth.
Right.
That will develop something of a systematic way to achieve this particular plasticity.
Right.
Otherwise, it's there are 27, but 14, but I don't really understand who is doing the job and why, unless you write the rule.
Yeah. So I said, like in the paper, that's basically that's what the text of the paper is. So the text of the paper is, in order to get this plasticity rule, we need to satisfy these constraints.
But and then this means that alpha should be here and beta should
Right.
be there.
Right.
Yeah.
Yeah.
Table of rules.
Yeah, I mean it's not a table. So when we plot it like this, so we just we use particular examples that satisfy the constraints. So we show what those values are. Yeah.
זה עושה לך פרדיקציה גם למה היית מצפה שאלה עצמם הפרמטרים, למה היית מצפה שיהיה יותר פרובability.
Right. Like for me, it's easiest just to look at these because these pictures sort of define the rule. Like I can give you a set of equations, but if you look at these pictures, it's clear, right? So if this goes up above this threshold, then it becomes depression, and that sort of thing. So to my brain, it's much easier to think in terms of these bar plots than to think in terms of equations.
So for example, this parameter now.
Yeah.
What it represents is the amount of calcium that is inserted in the synapse.
Yeah, all synapses, because it's a global signal. Yeah.
It's the same global signal in all neurons. But
not in all, right? It's basically all synapses, right? You have a postsynaptic action potential, and we assume it's not really true in biology, but we assume that all synapses get the same amount of calcium from that action potential, and that amount of calcium is 0.6.
So this is
right, which is what this is.
Exactly to say is that in an actual neuron, you might have this parameter be low for some of the synapses because it is very far away from the soma, and it might have this parameter high for a very proximal synapse. Okay, so it's like you have two different synapses in two different rules in the same neuron. Okay, so one neuron behaves according to this, another one according to this, because these parameters are actually as if dynamically changing as a function of the dendritic location.
Right. So I 100% agree with you.
I'm not. Okay. Just to clarify.
Yeah.
This parameter is the amount of calcium that is inserted into the synapse when a presynaptic activation occurs.
Right.
So that is also a thing that could be a function of the synaptic width, for example.
Okay. So I actually, I want to say something about this. So if you will notice, the equation for local calcium is alpha times x, right? So it's a function of the input. It is not a function of the synaptic weight.
but
Oh.
it's not, yeah.
Okay, why? So there are two
You
reasons.
mean like in biology or in my model? Why?
So
Why in biology?
so I have an answer for biology and I have an answer for the model. I will start with the answer for the model and then I will go with the answer to biology.
The model is because it's written there.
Okay.
Yeah. No, but
Let's go to
okay,
it.
no, but why did we decide? In other words, why did we decide that the local calcium should be only dependent on the input strength and not on the weight? Because if the local calcium is dependent on the weight, then that creates feedback loops, right? Because then you don't know how much calcium you're getting each time you have a presynaptic input. Because you imagine you potentiate a synapse, right? Right, because
But
something
this is
happened
like
that
a-
potentiates the
this is
synapse.
very complicated. It makes my model more complicated. This is
Yes.
the algorithm.
Right. So that is the computational reason.
Mhm.
Now, the biological reason. I like the biological reason.
This is the only
Okay,
one.
I will explain the biological reason. The biological reason is, like we said, calcium comes in through NMDA receptors. Okay, what does plasticity do? Plasticity increases the number of AMPA receptors, not NMDA receptors. So as a first approximation, hold on, I know what you're going to say. So it is true. NMDA receptors are voltage gated. So in principle, if you have enough AMPA receptors and you are in the superlinear regime of the NMDA receptor, it's true that more AMPA receptors will cause the NMDA receptor conductance to be larger. However, we're assuming that we're working in the linear regime of the NMDA receptor, which is a reasonable assumption if you're not in the regime where you have a lot of activity. Right. So people normally think that in order to get an NMDA spike, you really need a lot of synapses or clustered synapses. There's even I presented a paper, I don't know, a semester ago or something like that, where they actually did this experiment and they showed how many synapses you need in order to get an NMDA spike. I would say this is a controversial subject. Like people used to think that you need to have a cluster of 8,
But
right?
this is a very different thing. An NMDA spike on the dendrite, and an NMDA spike or an NMDA activation inside the spine. This is a very different thing, and the thresholds are likely very different. Maybe you can say.
No, so I do not think I agree. In other words, in NM, you will see in at least in terms of the no, I disagree with that. No, you should see, if you have an NMDA spike, you should see it in the dendrite. Because an NMDA spike.
A single sign. It could be the case.
Yeah.
That every time a synapse is activated, an NMDA spike occurs within the spine, and you don't see anything substantial or something very close to large NMDA activation inside.
Yeah. So I would say I've also I should say yeah. So yeah. I've also done modeling of this right with Menachem, and that doesn't happen. Right. If you have, because an NMDA spike is giant and also it's long. And you don't have that much attenuation through the spine. Like you have some attenuation, it'll be like whatever, a few millivolts, something like that. But you will see it. You will see it in the dendrite, for sure.
But what do you mean like the linear regime of the NMDA? Receptor locally on the spine. Like it should not be linear.
Is no that right, you think of that NMDA nonlinear.
Only one synapse on neuron,
Yeah.
only one synapse.
Yeah.
With NMDA receptor and like an infinite number of AMPA receptors. Okay.
Okay.
Like a sequence of neurons that each time you get more and more AMPA. Okay. So what will be the curve of the voltage as a function of number of AMPA receptors? There is
No,
is
so
there a linear part of this
No,
curve?
it's
So-
not linear. I think it means that fixed.
no, when I say right, the NMDA function is a sigmoid, right? So when I say linear, I mean before you hit the vertical part of the sigmoid, right? So
No, I think you
Yeah.
wanted the up. What
no, the lower. I'm in the lower part.
the upper part.
This one.
Yeah, exactly.
So the first part is before the NMDA even opens, right?
Yeah.
Exactly.
But
No, it's not open.
That part is where the NMDA is variable, and what Tove is talking about is actually after that part when NMDA is constant.
no, I'm not.
The current through
Okay,
NMDA
when I
is
say linear, I'm okay. I'm sort of thinking of that your NMDA activation curve is like that. So it's not good, but you could call it linear, you could call it like constant. It's not changing much over here.
So
Yeah.
here it's not open, right?
It's
It
barely
stays-
open.
It stays closed until the voltage is big enough, and this point, once you have more inputs, it will be open more. So you are referring to the part where there is no NMDA.
No, there
No, I think-
there is an
I think
MDA,
it's
there is
referring to the
conductance.
part where, like you said, there is as if infinite amount of AMPA receptor. Every presynaptic spike maximally inserts a maximum amount, alpha amount of calcium into this node. And this is a constant amount of calcium every time the presynaptic spike occurs. And it is irrespective of the postsynaptic activity.
Yes, that right. So that is
So
based, yeah.
it should be alpha, not
Exactly.
alpha XI.
Oh,
No, because it depends on, no,
But the
it
X are
depends on the
binary.
input.
but the
Right,
X's
you
are
have-
binary. X's are binary.
It's either
Yeah,
zero
no, because it's also, right, the NMDA activation is also a function of the presynaptic input.
X are binary.
Give me- give me-
It can only either
Yeah.
exist or don't.
If I understand well,
Yeah.
we are actually looking at the NMDA current. Which is, this is what really matters, because you look at the current, calcium current.
Right,
It
it's
goes
calcium
to-
current, that's important, yeah.
No, NMDA current, let's call it NMDA
Right.
current, I. The current that goes through NMDA receptor, some percentage of it is calcium. Okay? And the voltage, and this is the voltage. And this is the current. And it looks something like that, yeah? This is the reversal of the NMDA current, which that's a zero. This is minus, I don't know, what, 70 millivolts, let's say. Resting. Okay, so there is a certain place where the NMDA, when the voltage is big enough, there is more and more NMDA current. Yes, and this is the calcium current we talked about, the percentage wise. 20% of the current is this current. So this is the VI curve of the NMDA. So if you're here, as Ido said, there is no opening of the NMDA, because there is no NMDA current, there is no calcium current. But if you are here, where the voltage is already affecting the opening of the NMDA channel, if you are here, then if your voltage is, I don't know what number it is, let's say 20 millivolts, it will give you this amount of current. And if the EPSP at the spine head is 30 millivolts, it will give you this. Yeah. So that's the question. So you're not looking at this regime,
Yeah.
because otherwise you're looking at some flat regime with some, I don't know, this kind of a regime which is
Exactly.
flat over this.
Exactly.
This
This
below
is
threshold.
the model.
Whatever threat, no,
Flat-
below
flat
threshold, there is no
constant
current.
current. It's like
No, there is
when
no
there is no
current.
input
There's
at
no
all,
constant.
it is zero, and when there is some input, it
It's a
is
fixed,
flat.
that's a flat number that is this alpha. Whatever.
Exactly. So,
But then it should
That's
not
the way
be-
to think, no?
Yeah,
That's
right,
that's
we're
the
thinking
IV
it's
curve of
flat.
the NMDA.
Yeah, so we're thinking that it's yeah, approximately flat as a function of the
Why?
of the voltage.
But then it should be alpha, not alpha XI.
No, because it
XI
depends on
binary.
also on the state. So this is what it
or
is.
activity or not.
Yeah, for now it's binary. So sometimes sometimes it does matter because of the but if you have a rate model, a rate model it also matters, right? If you have higher frequency presynaptic input,
If you have a
you'll
function
open.
with two options, it can be linear, sublinear, superlinear, whatever you want it to be.
But this is not actually the reason I asked the question. Can you go back to the previous one?
Yeah.
This one.
Yeah.
So basically what I wanted to say is that alpha and gamma
Yeah.
are things that are dynamic on the neuron. That this is actually in real life, in actual biology,
Yeah.
this is dependent also on the synapse and also on the nearby activity. This is like a heterosynaptic plasticity. This is dependent on your location on the dendrite, and it can change inside the neuron. So inside the same neuron, you can have this and this at the same time. And this value, this alpha, so this thing can go up and down as a function of just learning, the things that changing over time. But everything else basically stays the same. So these two things can change inside the neuron as a function of location, can change as a function of time, but nonetheless, all of these options are kept the same. So for strong synapses, these would be maybe large values. for weak synapses, these will be small values. And it's like for synapses that have small values, they behave in some way. For synapses that have very large synapses, they behave in a different ways, as if a different plasticity rule is actually applied on it.
Right. So that,
I
yes,
think the model is still extremely useful for this case.
right.
You just need to remember the.
I think, why do you say that the theta D and theta P can change inside the neuron?
Not that the
No, no.
alpha and gamma.
Yeah, they can change, but why theta can change?
I did not say anything. So
They-
I think it
yeah.
can also.
Yeah, so they can
Just
totally
change
change.
the line, yeah.
Right, like imagine, yeah. Yeah, because because whether like the calcium thresholds presumably for plasticity presumably depend on the concentrations of second messengers like CAMK2 and calcineurin. So I think it's yeah, it's totally reasonable for, you know, if you have you know, this much CAMK2 and that much calcineurin, that's one set of thresholds, and then if you have a different amount, that's a different set of
And
thresholds.
also,
Yeah.
can also
And the buffering, right?
You can consider also the change in alpha by the magnesium concentration in the cellular.
Sure. Yeah.
Like this, and then it-
But
Yeah.
this, we, at least we think
It's like-
is fixed.
Well, okay, I should say they actually in the
Inside the
in
biological organism, it's fixed.
in the paper that I'm
Extracellular state.
yeah. Yeah, so in the
Depending what you eat.
Yeah, and that's
yeah.
So it's not has any function, the magnesium like that?
I don't know if calcium can change, magnesium.
Magnesium. It's
Magnesium can
affecting the
change
NMDA.
magnesium. I can tell you that, that when, at least in the past, when women were pregnant, and they wanted to stop the early delivery, they used to inject a lot of magnesium in the blood, which must increase the whole magnesium over the whole body, and this will reduce the contractions, because it fights calcium. Yeah? So it's an antagonist to calcium. It's very helpful for this. I know this is a treatment that was used for that. I don't know if it's still doing today, but it was very effective to delay contraction.
You gotta go.
in women
Okay.
that are,
You have to go.
you know,
Thanks for coming. Yeah. Okay, so we
They need many much
ששיתפתי שהיה במראה.
we are assuming
ואז כזה הוספתי עוד נורי וג'ינג'ר.
and one point I want to make. Okay. Okay, I want.
זה לא קשה להפוך את זה לכיוונים.
Okay. Yeah. Okay. I want to make a point with respect to this NMDA thing. That I agree that you know, maybe it is valuable to think of the calcium that comes from the NMDA from the additional voltage, and you can get that via the heterosynaptic plasticity. So if you notice, the heterosynaptic calcium source is beta times the sum of the weighted sum of all of the synapses. So in fact, you are getting, for any given synapse, you're also getting that synapse's weighted contribution, right? So in a sense, you can think of the heterosynaptic plasticity as not just coming from the voltage-gated calcium channel, but the sort of the net depolarization that you see in the dendrite, and that can also be due to the NMDA receptor voltage dependence. So
This don't
yeah.
depend on the specific W in the specific synapse. It depends on the sum of the synapses and their activity.
Right. So this is a perspective. Yeah. Right. So that is correct. But this is a perspective where you can think of it as like dendritic depolarization. Right. So it takes into account, let's say, the dendritic depolarization aspect of the NMDA receptor activation, maybe not the local activation as much. Yeah.
So I had a question about this one.
This one?
Yeah, so maybe you should also just consider the ones which are stable. Like most of these are not, I won't believe that really exist, because they mean all the synapses will go to zero very soon or to infinity. So like, You see what I mean?
But it could be that there is the homeostatic mechanism not implemented in this way, but in a different way.
Yeah.
For example.
We do, by the way,
Total amount of synaptic weights is fixed all the time.
yeah. I talk about homeostatic plasticity shortly.
Yeah,
Not-
I
yeah.
mean, if you like assume beta is 0, still you can the first 3 rules that they don't make sense. Also the fourth one and the fifth one. Like you have to have a synapse that can also grow and
Yeah.
Okay.
like if you take the first rule, if the
What, you don't think-
nothing happens. There's no plasticity.
Yeah, which in some neurons probably is the case, right? You don't want all of your neurons to undergo plasticity. Some neurons, maybe you want them to be stable, at least as a function of presynaptic and postsynaptic activity. And also, by the way, the paper that I'm going to present actually makes the argument that that there is no plasticity. No, so then they make so it's about philopodia, and they basically say that plasticity only happens in philopodia and not in regular synapses. When you're older. Okay. Very good. So the next thing that we're going to do, so all of this was assuming that we have binary inputs and binary outputs. Now we're going to shift to a rate model, and we're going to talk about frequency-dependent plasticity. Now, normally when people talk about frequency-dependent plasticity, they're talking about presynaptic frequency, right? So if you have a slow frequency input, you might depress the synapse. If you have a high frequency input, you potentiate the synapse. So that's the situation here, where it just depends on the local calcium. But in principle, if you believe that you get calcium from the postsynaptic spike, you should in principle also be able to have postsynaptic frequency dependent plasticity, right? So you can have the same thing with the postsynaptic spike. If you have higher right, so if you have slow frequency, or in this case, I guess it's medium frequency postsynaptic spiking, you get depression. If you have high frequency postsynaptic spiking, you have potentiation, right? Could be. And you can also have combinations of them, right? So you imagine, so in this case, you have fairly low rates of both presynaptic and postsynaptic input, you get depression. But if you have let's say your presynaptic input rate is 2 and your postsynaptic firing rate is 1. These are just like arbitrary units, but they can combine and give you potentiation, right? So you can have pre and postsynaptic frequency dependent plasticity rules if you're using a rate model. And here I just show that what happens if you change the different coefficients, how different pre and postsynaptic firing rates will affect the plasticity. Right, so this is the case where you only have presynaptic calcium. So in that case, everything depends on the presynaptic firing rate. In this case, you only have calcium from the postsynaptic spikes, so everything depends on the postsynaptic firing rate. And then you have these intermediate cases where here it sort of more leans towards the presynaptic, and here it leans more towards the postsynaptic. So again, this is just sort of a broader sort of view of potentially what can happen in plasticity than what people normally think about. And to what extent this happens in biology, I think there aren't really so many studies that have shown this, but I don't think that there are that many studies that have been looking for it either, right? So part of the purpose of making models is to make predictions that can then be tested and falsified or verified. And if it's false, it would be interesting to know why it's false, right?
People did report that frequency is a function of frequency.
Yeah.
Yeah,
Right. So this is very this is pretty standard, presynaptic only, right? So what I'm adding here is also postsynaptic frequency dependent, and also combination of presynaptic and post.
They didn't
This-
activate the presynaptic or the territory in this frequency on the input side, and also injected this frequency on the output side to check what this combination would do to the plasticity.
Right, or at least I should say I haven't seen it. It may exist, but I haven't seen it. There is, and there's one figure from a paper I have one panel from a figure by from a paper by Tigre. I forget who the first author was, with STDP they did a bit of that. So they did like one presynaptic, two postsynaptic, but in terms of frequency dependent, these difference values, I haven't seen it.
So
Yeah.
like in the post, if you have a spike, you have a spike. Does it matter? Like the calcium levels will be different if you have two spikes.
Yeah, of course. Right, because you're opening up the voltage gated calcium channels for longer.
So,
Yeah.
yeah, but by what you say that they have done, they did the combination of the two, essentially, because if you are injecting, you are not preventing backpropagation action potential to happen. From happening. Like you should do like current clamp, voltage clamp in the sun in order to check the first one.
I see what you're saying. Because you're saying if you just do like a high frequency protocol, maybe you're activating postsynaptic spikes. My sense is that usually they do something to prevent that from happening, or they activate it in a regime where you just don't get postsynaptic spikes. I'll have to look at the frequency dependent plasticity experimental papers again. But I think the assumption is that it's really just presynaptic input.
You get plasticity when there is no postsynaptic spike.
So
If you inject it, it will activate the synapse again and again and again, but do not allow action potential on the outside, on the output. Will the synapse change, no?
So I think, yes, I think that is the standard frequency dependent plasticity protocol. But I have to look at those papers again.
This is a high frequency stimulation. No?
Yeah.
But you need to do it.
But it's right, you need to make sure that it's not the postsynaptic spike that is going, it's high frequency, but what is the output? If the output is spikes, maybe this is the STDP. But if it's without spike, it's not STDP.
Yeah, but it makes sense. Like, if you have an NMDA spike, you have calcium.
If you have local NMDA spike in the dendrite, then you have maybe another signal plasticity signal.
Right. Because if you're just simulating a single spine, should you get enough voltage from that?
You need to give the answer. Like, your previous paper should give the answer. No?
I mean, it depends where it is. Like, so certainly, right. So certainly, if it is very distal synapse, you won't get a spike just from a presynaptic input because you'll hit reversal. You'll hit reversal and then you'll get attenuation.
So there will be no output spike.
Output spike, yeah. For a proximal synapse, potentially, yeah, like you in theory, you can get a
I think
postsynaptic
people
spike.
did it, you
Yeah.
know, for example, Spruceton did do not exactly what you suggested, but Spruceton injected PPS in order to avoid the backpropagation. So there was no backpropagation. There was no spike, but we did show local plasticity.
So there
There
is
is some local, whatever, I don't know what, local voltage, local depolarization, local NDA, but some local thing happened that without the backpropagation, you get plasticity. This thing of
But how do you have presynaptic spike?
no, it's a very local,
Wait, can we give me page?
no, the PPX is packed on the stoma of the postsynaptic cell or the beginning of the dendrite. So it avoids the backpropagation, but it doesn't avoid the stimulation. It's not a global PPX, it's a local. It's a paper from 10 years ago. It shows that the signal of each signal not necessarily need to be the backpropagation.
Right, that sounds familiar. You probably have that in the introduction of your thesis. Yeah. Okay. So that's pre and post. Okay, very good. So now we're going to move to heterosynaptic plasticity. This one is a little bit weird. Chaim Sampolinsky also asked me, "Is like, what can you do with heterosynaptic plasticity?" So this is the task that I came up with. The task that I came up with is, so a neuron is getting input patterns. There's one pattern which we're going to call the signal pattern, which is getting repeatedly. So you see the signal pattern and then it shows up again. And then there are other patterns that happen, but they're basically just random. And what we want the neuron to do is that we want the neuron to recognize that this signal pattern is sort of like this regularly repeating pattern, and we want the neuron to eventually fire in response to this signal pattern. Okay, so the way that we do that is like this. We have, let's see if I remember this. Okay, so in every pattern that you get, we don't have calcium from the postsynaptic spike. We only care about the local calcium, and we care about the activity from the other synapses. So if you are, and I should say all of these patterns have the same density. So if you're an inactive synapse, inactive synapse, so you're one of these synapses that aren't firing, but there are other synapses that are firing. So you're going to get a certain amount of calcium, of heterosynaptic calcium from the other synapses. And if you just have that heterosynaptic calcium and you yourself, that synapse isn't firing, so you get depression. But if you are firing, so then you get that synapse potentiates. So effectively what this means is that every time one of these patterns comes in, so all of the active synapses potentiate and all of the inactive synapses depress. Okay, so how does that help us? The idea is that if you have a commonly repeating pattern, the synapses in that pattern are going to potentiate, and the other synapses are going to be depressed. Now, when you have these noise patterns, they're also going to depress other synapses, including the signal synapses. But because the signal pattern is coming more often, so on average, all of the other sort of potentiations will average out, and will average out with the depressions, and you'll be left with the signal pattern. So to illustrate that we get this, but so these are each of the patterns, I should say. So they're labeled with S or N for signal for noise. So this is what the signal pattern looks like. It's the same as this. And this is the output of the neuron. So initially, so whenever you have an X here, that means it's a false negative, right? So it's a signal and it should have fired. So initially, neuron is firing in response to nothing, so neither the signal or the noise. But eventually you see that it correctly fires at the signal pattern. So you have this red circles, and it doesn't fire in response to the noise pattern. So it succeeds to do this task. And you also see this in the synaptic weights, that over time, the synaptic weights converge to this signal pattern, right? And that's why eventually you get spikes here, because those weights are the weights that are eventually potentiated. Oh, Tom? Right. So the main reason why this is different than Hebbian is because it's not spike dependent. Yeah. So right. So in terms of the practical relevance, why a neuron will want to do this, so one of the problems with Hebbian learning is that you have to a priori know what you want. Right. So how do we know that we should potentiate this particular input pattern? Well, some people do it with a supervisor, in which case it's not really Hebbian, it's supervisory, or just like randomly, it happens to be that this pattern has more synapses, or those synapses happen to be larger weights. That's what we showed in the initial case. Really, right, what produced the spike was just like randomly, sometimes the patterns were larger. Here, that's not necessary. So here, what tells the synapses to increase, or say the reason why they eventually increase their weight over time is just because it's presented many times to the neuron, right? As opposed to with Hebbian plasticity, if you start out that that input pattern isn't producing a spike, you're never going to be able to produce a spike from that input pattern.
Okay, so I have a question here. So
Yeah,
it's gonna be extremely dependent on the frequency of your pattern, right?
correct.
And the strength of the noise. Like how many synapses are activating in the noise.
Also correct. Right. So I should say this was the hardest one to do, right? So in order to get this to work, you have to make a lot of assumptions. So yes, we enforced that the sparsity of the signal and the noise was the same.
Also,
You
will fire for every pattern that contains the signal. Right?
correct.
So you want all the other ways to be like minus infinity.
No, in other words, first of all, if you enforce that the sparsity is constant, so you will never have any pattern that contains the signal will be the signal. Yeah.
Okay.
Yeah. So again, this is a little bit artificial, but it just shows, something that you can do with heterosynaptic plasticity. Okay.
You chose the.
Yeah.
This is mathematically, this is the Oya rule.
This is
The Oya rule.
the
Oya rule.
Oya rule. It
You
is.
know exactly what the Oya rule does. Mathematically.
I mean, right. So it does PCA. I'm a little bit.
Should be doing ICA.
Yeah.
תעלה למעלה רגע, את ההגדרה של ההטרוסינפטיק פלסטיסיטי. This is if the neuron was an output neuron, y equals w transpose x. Right?
No, well, there's a threshold here.
I agree, but in Oya neuron, there is no spiking, there's only a linear neuron, the linear output, which is your w transpose x. This is the linear output. And the input, so here you get the supervising signal in the when beta is larger than 0 from the linear component of the summing of the matrix of the inputs, and therefore this is mathematically 1-to-1.
We will have to discuss it because here the heterosynaptic calcium. So you always have the same amount of heterosynaptic calcium because we enforce that the sparsity is constant. Yeah. Okay. Well, let's discuss it because that's important.
Did you choose here W or you just random?
We chose the W such that it would work with the sparsity. the initial W.
I wonder if you
Yeah.
just choose random W, you could find a pattern that is a signal and a pattern that is not.
Yes. It must have, maybe it's a כוונן כמה דברים.
כן, אז הסיגנל תמיד יהיה אחד מכל הפאטרנים, והנויז תמיד יהיה בגודל של מספר סינפסות פחות. על פניו.
זה פרמטר נוסף שביחד עם הנויז, כאילו כמה פריקונסי של הסיגנל וכמה עוצמה של הנויז, זה כאילו פרמטר שבא איתם ביחד, ה-initial W.
Sorry, I'm gonna request that you talk in English just because I'm gonna be uploading this. So
Yeah,
we want people to hear your questions.
It's
No, but if you
another
random choose a matrix, W,
a random?
a random matrix, it would find you a single signal, and all the other patterns will be noise, right?
No, if you present any random signal, the W will converge to the signal as a function of time for any random signal. That
W is not
slightly
function?
more. No, W is changing
Oh,
as a
okay.
function of.
Yeah.
And the time it will take it to converge is dependent on the initial W's, the strength of the noise, and the frequency of the signal.
Correct. Yeah. So imagine if you have two signals, right? So you imagine you have two patterns that are 50%. You might have some problems. And you won't have problems. Yeah. Yeah. So
No, but
But
maybe
again, you know exactly what the Oya will do.
right. Oya rule, if
Exactly
you have
the
multiple neuron, right? You have multiple neurons, and it will be lateral inhibition. So right, something like that.
No, a single Oya
Yeah.
without lateral. Single neuron Oya.
Yeah.
If you have two signals, one is a probability P, one is probability Q, and all the rest is random numbers with probability Y minus P minus Q, you can calculate the PCA of all those X's, and this will be your final weight.
Interesting. Okay. We should do that maybe.
which is basically the sum of the two signals minus the average of the nodes. This is the piece.
Okay, so,
I just
so eventually, as long as you're correcting the threshold of the spike correctly, you can save patterns as much as you want.
What do you mean of PCA? Because you have here like 10.
What
It's
is
like
PCA?
you take the 10 pieces of 10-dimensional input. So it's like
No, the first page is one. The OIA gets you the first page.
It's the most probable one, because it's the most straight one. that you got in.
What is the X here? What is the probability distribution of the X? Like a 10-dimensional vector of X's, given values. What does it mean to do a PCA on it? It's PCA on this.
so it's on the first PC.
Like that. When you get the first PC, it will be your final W.
Right. So I guess, right, if you only have one pattern, so then the first PC is just that pattern. But if you have two patterns, then it's what it's basically like the average of the
Yeah.
patterns, I guess,
Yeah.
something like that.
Depends on the frequency.
It's like
If
like
the
this.
frequency is the same.
Two patterns and
So
random
it'll
noise.
be a weighted average.
Random noise is here, let's say, two patterns. What is the component? It's like you calculate the average of this, you calculate the average of the positive. Oh, no, this will be the PC.
Okay, so this is actually useful. Okay, very good. Yeah, we'll have to discuss it more. Okay, so that's unsupervised learning, possibly PCA. Okay, we're now going to do we're gonna do this this hippocampal place field formation thing, but this is a very abstract version. So to remind you again of the work of Aaron and Christine and Jeff McGee and all those people in that lab, you have a mouse running on a circular track. I'd say there are some sensory cues, and we're looking at the hippocampus at CA1. Right, CA1 neurons in the hippocampus, and you have sensory input is coming in through the CA3, and you have a supervisory signal coming in from the entorhinal cortex. And basically, wherever the mouse is on the track, so let's say it's at the circle, if you have a supervisory signal come in from the cortex at the time when it's at the circle, you can turn this neuron into a place cell with a place field for that location where the mouse is at, which in between the circle and the triangle or whatever. And so the supervisory signal can create a place field. And also if you have another supervisory signal and the mouse is at a different location on the track, you can create a place field at a different location. That's a second induction. And this is the voltage that we see experimentally. So initially there's no you just have baseline activity, then you see the plateau potential, you create a place field, then you create another induction, so another supervisory signal, and now you create a new place field around where that induction was. Okay, so we're going to do we're going to ignore time. We're going to ignore all of these temporal aspects, the fact that you can have two place fields, and we'll just say, okay, this is how it works. That the supervisory signal creates the supervisory signal creates a place field. In other words, it potentiates all of the inputs that were active at the same time, and it depresses all of the other inputs. So we call this 1SFF for one-shot flip-flop. They call it BTSP for behavioral timescale plasticity. I like our acronym better, right? Because it's basically if you think about like a computer register, it's like a write signal, right? So you have your input, and the supervisory signal says, so let's say it's a binary vector of like 0, 1, 0. So the supervisory signal says, okay, I want you to write this signal 0, 1, 0 to the synapses by potentiating them. And we make it very binary here. We use a special version of the plasticity rule, which immediately potentiates and depresses. This just illustrates that it's not very, yeah. So basically, if you have a depressive signal, it immediately depresses everything to 0. If you have a potentiative signal, immediately potentiates everything. Another depressive signal immediately depresses things again. So it's a binary sort of flip-flop switch. Yeah.
Just comment that in their work,
Yeah.
this paper, they argue that the change in W is a function of the initial W.
Yes, I am aware of that. In my other paper with Lee, we also say that that is true, and we have a very elaborate model of that. Here, it isn't because what we're trying to do here is we're trying to extract kind of like the computational principle without all of the little subtleties of how exactly it works. And to me, what is the computational principle of this kind of plasticity? It's that we can have a supervising signal that writes the input to the synapses, and then you have the supervising signal again, and it writes a different input to the synapses. It's a write signal. That's how I think about it. Now, this may not be exactly how it works in the hippocampus, but this is sort of a canonical model for how you can implement that kind of plasticity. So the way that this works is a very similar idea to Hebbian plasticity, except that now we're using this external supervisory signal, this plateau, instead of the postsynaptic spike, right? So if you only have an active synapse, so the active synapse by itself cannot induce plasticity. If you have the plateau, but you're an inactive synapse, so the calcium from the plateau depresses you. But if you're an active synapse and you come at the same time as the plateau, so that synapse will depress. So to illustrate how this works, so we're simulating our mouse running. So there are 3 locations on the track: 0, 1, 2, and 3. Each of them are indicated by a different binary pattern, right? So it's just like repetitively, running across the track, and then we will randomly activate the supervisor. So the first time we activate the supervisor, it is at location 0. So you see that you have this increase of calcium at location 0. Some of those synapses are active, some of them are inactive. And immediately, because this is an immediate kind of rule, immediately all of the weights become identical to that input pattern, right? So you're writing the weights to the input patterns, then you do it again at location 3. Again, you write the weights and so on. And because you've written these, you potentiated these synaptic weights, so your voltage, the output of the spiking output of the neuron, also reflects where that place field is, right? So after the first induction location, it spikes at location 0. After the second induction, it spikes at location 3, and so on. So that is behavioral timescale plasticity, one-shot flip-flop plasticity. Okay, homeostatic plasticity. Idea of homeostatic plasticity is for computational simplicity here. The idea is that you have a neuron that physically it is possible for this neuron to fire in between a minimum and a maximum rate. So physically, let's say the neuron can fire at 0 hertz, right? It cannot fire at all. Or let's say maximally it can fire at, I don't know, 100 hertz. But the system wants the neuron to fire, let's say, between 10 and 20 hertz, let's say. So yeah, I'm sorry, this is a little bit tiny. So the way that we illustrate that is here. This is the output of the neuron. We have these 2 dotted lines. Again, they're a little bit hard to see. So this top dotted line is the maximum target. So it's the largest target firing rate, and this bottom dotted line is the minimum target firing rate. And what we want is the output of the neuron. This is a rate model neuron to be within that minimum and maximum target range. Okay, it's going to be a bit complicated to explain how this circuit works. So maybe I won't explain it for the moment. I'll just say that generally there are 2 ways to implement this kind of homeostatic plasticity. One of them is where you have an internal depression mechanism and an external potentiation mechanism. So what do I mean by an internal depressive mechanism? What I mean is that, if the neuron is firing at too high of a rate, so that's this case here, the neuron is firing at too high of a rate, it will depress just because it's internally over its depression threshold. But if the neuron is not firing enough, so the neuron is firing weakly, what you do is you have a disinhibitory circuit for the supervising signal. So basically the supervising signal sends a potentiative signal to the neuron whenever it's not firing enough. So that's this sort of internal depression, external potentiation. That's
Can
this
they-
circuit.
They can
Yeah.
both be internal.
No, so you can't do them both internally. It because because
You mean like
Yeah.
mechanism in a biological neuron, it cannot be. This mechanism cannot happen internally inside the neuron.
no,
without
okay,
the
no,
atom?
so hold on, okay. In one slide, I'm going to show you how it actually works in biology, which is not how it works here. However, with this mechanism that we're using for calcium-based plasticity, you need to have an external supervisor just because of the logic of homeostatic plasticity. And the other way of implementing this circuit is that you have a supervisor for both potentiation and depression. So you have a direct circuit for the depression and a disinhibitory circuit for the potentiation. And that's how you implement it. Now, I should also say there are two different, within each of these circuit models, there are also two different strategies. So there is what I call a global homeostatic strategy and a targeted homeostatic strategy. What do I mean? So global homeostatic strategy means that if you are, let's say you're firing at too high of a rate, you depress all of the synapses. Whereas a targeted homeostatic strategy would be that you only depress or potentiate those synapses that were active at the time when you had a bad firing rate.
Yeah, like the most straightforward way is just to change the net, right? So if the net had some bias term, and then
What do you mean? What do you mean the net?
So you have beta, right? W times transpose times X times beta, right?
So
if you have
here there's no heterosynaptic calcium. We only have the local, we have backpropagating action potential, and we have the supervising signal.
Yeah, I know. But if I'm changing the net, the C net,
C total, yeah.
yeah, C total, to have a bias term, which is the homeostatic plasticity, and then beta is just how much I will change towards this this value, right? So it's either I'm above it or below it. I'm just trying to reach beta. So if W times X is larger than beta, I just want to depress. And if it's smaller than beta, I want to potentiate.
It's large. Okay, that's how it. Let me get to the next slide, because that's like how it works in biology. But yeah, just so one thing at a time here. I want to show that this actually works. Again, it's a little bit hard to see here. I don't know if I can zoom in, but basically we start out. Well, the way that we illustrate how this homeostatic plasticity works is that we initialize the synapses such that the even numbered synapses have a very low weight and the odd weighted synapses have a very high weight. And we present either even and odd patterns to the neuron, right? So the even patterns will initially be too weak. And the odd patterns, when I say odd, I mean the odd numbered synapses are active. So the odd patterns will initially be too strong, right? And so we have both of them. So these are the two high patterns, and here blue, those are the two low patterns. And eventually, due to this homeostatic mechanism, all of these circuit mechanisms and both the targeted and the global strategy eventually converge to be within target range. So that is if you try to implement it with our calcium rule. Now, how does it actually work in biology? It actually works in a totally different way, but actually not totally different. What do I mean by that? So yes.
What you say here is that there are certain, let's call them circuit motifs, and
Yeah.
if you have a particular connection, a particular plasticity rule on a type of connection from one type of neuron to another type of neuron within that motif, it can effectively, even without an internal mechanism of the cell, it can effectively create a homeostatic plasticity, a regularizing thing within the circuit.
Exactly.
This is example one, this is example two, and these both can happen with, interesting examples that we can now maybe look for in biology. So the effective functionality of these types of circuit is a homeostatic plasticity, and they are implemented in a circuit way and not in an intrinsic mechanism.
Right. Right, and I should say, so these use the standard mechanisms of the calcium control hypothesis. Okay, how does homeostatic plasticity actually work in biology? Not like this, but it also uses calcium signaling. So, so there is a totally different calcium pathway for homeostatic plasticity. At least this is what Trigiano claims, and she's like the Gina Trigiano. She's at Brandeis. She's the homeostatic plasticity person. So I should say homeostatic plasticity usually occurs over long time scales in the order of hours or even days. If you force a neuron to fire less or to fire more, so eventually you'll have scaling up or scaling down of the synaptic weights. So her model of how this works is that in the soma of a neuron, all right, I think this is actually soma as opposed to all these other processes where really the activity is happening at the spine. So here, these processes are happening at the soma, and normally, if the neuron is firing at the target rate, so there will be a balance between say the potentiative and the depressive mechanisms, CAMK2, calcineurin, or whatever it is. It may not be that in this mechanism, but you have these, right, depression and potentiative processes. If the neuron is firing at too low of a rate, the neuron notices that it's getting less calcium than usual, because the soma also has, I guess, some calcium receptors. It senses via calcium that there's less firing, so so this lower level of calcium is actually what instigates certain molecular processes that scale up the synaptic weights, where if you have a too high of a firing rate, you have a lot of calcium, so you will you'll have these scaling down mechanisms that will decrease the synaptic weight. So if you were to draw this like the calcium control hypothesis, can they see well, okay. So if you were to draw this model of somatic homeostatic calcium scaling, okay, have an eraser. Sorry, David. The convolutional neural network is
Erased. On the face of the brain.
okay. So this is, let's see, this is your delta. I should have put this on the slide, but whatever. So in your target range, that will be the middle. And then if your calcium is too low, then you increase the synaptic weight, right? And if your calcium is too high, then you decrease synaptic weight. Actually, okay, this will be 0, right? So this is 0, so no change here. This is depression, this is potentiation, right? And if your calcium is too high, then you decrease the synaptic weight, right? So this is the calcium control hypothesis for homeostatic plasticity as described by Trigiano, and this is a somatic thing that involves different second messengers. It happens over longer time processes, but it's still calcium dependent, and it's just a different version of the calcium control hypothesis.
Yeah,
So
except it's probably not steps. I think they are saying it's a linear case. So I don't think they're claiming it's steps. I think they're claiming something like that.
no, I don't. Oh, well,
They speak about multiplicative.
well, so
Multiplicative mechanism. So if the firing, the firing rate is twice than expected, so there is a set point that you want the neuron to come back to this regular, let's say 10 hertz. If it's 20 hertz, so then you will decrease the W of the synapse by a factor of 3, let's say. Yeah, so it's a multiplicator. If it's 40 hertz, then you reduce the W by a factor of 4. So they speak of the nice thing that they show is that it's multiplicative. That all the synapses are going independently of their initial weight. Independently, all the synapses are going scaled up or scaled down by the same factor, independent on the initial state. But linearly, how far is the set point relative to the actual activity? So eventually, it always comes back. But it's linear with the divergence. the more it is divergent from the set point, the more correction you need for.
I see. But
That's
it's
what they
still,
show.
right, but still within this region, it should be flat, right? So it's more something like this. So,
Okay.
and
Could be.
yeah,
זה artificial,
עבודות מלפני 10 שנים, כמו שאומר כאן. הם לוקחים ומסתכלים על הם עושים את הסטטיסטיקה, אני זוכר עכשיו נכון, כן? הם מסתכלים על הסטטיסטיקה של העוצמות הסינפטיות, שבאופן ספונטני אתה רושמים EPSP, קטנים, גדולים, גדולים, קטנים, קטנים, גדולים, גדולים, קטנים, מה שיש באופן ספונטני. הם עושים אוטומטית התפלגות של העוצמה של ה-EPSP, של הגודל של ה-EPSP בבייסליין, נגיד שזה בייסליין. עכשיו הם מגרים את התא הזה בכוח, כן? וכזאת תקופה, זה הרבה זמן, זה גירוי מוגבר. מגרים, עוזבים את הגירוי, בסלייס, עוזבים את הגירוי, ועכשיו עושים שום סטטיסטיקה על הסינפסות, על הגובה של ה-EPSP והספונטני. הם מראים שהכל, העקומה הזאת, העקומה של העוצמה של הסינפסות בבייסליין, הכל זז באיזשהו מולטיפליקיישן. כל העקומה זזה בהכפלה, כן. אחר כך הם עושים את המקרה השני, שבו הם שמים TTX או לא יודע מה, בשביל להקטין את הסיכוי של התא יורה. אז התא לא יורה, באיזו תקופה של חצי שעה או שעה, אלא אם התא בכלל ליצור ספייקים ספונטניים, ואז הם שוב בודקים, הם רואים שהכל זז באופן הכי ימינה בעוצמה ממוצע של הסינפסות. זה היה עבודה מעניינת, יש להם איזה תיקון כזה. הסינפסות מרגישות אם אתה ירה יותר מדי נפשות ביחד בסקאלה. אם אתה ירה פחות מדי, אז הם מחשפות את הסינפסות בשביל שירה במה שצריך לראות. סט של עבודות יפות.
okay. So this is where we're already at the final one. So we're going to do the perceptron here.
Just what I wanted to say,
Yeah.
you can implement it. This kind of rule,
Yeah.
if you're just taking W transpose X times beta minus, I don't know, this should be the threshold, right? So, and the beta should be negative. And then if you're above this T, right? So you'll go the other direction, you will depress, and vice versa, because this B and this minus T will do this flip-flop you're talking about. Right? It's
Yeah.
going to change the sign.
Except you're not allowed to have negative calcium. That's against the rules. No, it could be. I should say, like, I'm sure that there are mechanisms in the cell that can potentially like reduce the amount of calcium that you have. But in this model, the coefficients are not allowed to be negative because that's how it works. Okay. Okay, so we're going to do the perceptron. This is the coup de grace over here. We want so that you can implement perceptron learning with calcium, because that means if you can do the perceptron, then maybe you can do neural networks. Okay, so maybe back propagation is still hard, but okay. So perceptron learning rule, to remind you, is that is a supervised learning rule. So you have a target. Target is 0 or 1. The target we call Y. So in other words, we want the cell to either fire or not fire, and the cell's output is defined by Y hat. You can't see the hat so well here, right? So the cell either fires or not fires, and you either want it to fire or not fire. So there are basically 4 different cases, right? False positive, true positive, false negative, false positive. So you need to make sure via the calcium concentration that all of these cases are satisfied. Now I should say that because we're using the fixed point learning rule, so we're not doing exactly the normal perceptron learning rule, but we're doing this sort of asymptotic learning rule. So where the perceptron would tell you to just go up linearly, the FPLR rule sort of tells you to go up asymptotically, but basically conceptually it's the same, right? The idea is that if you have a false negative, in other words, you wanted the neuron to fire and it didn't, so you increase the synaptic weights proportional to the inputs. If you have a false positive, right? So the neuron fired and it wasn't supposed to, so you decrease the synaptic weights proportional to the inputs, and so you eventually do that over a number of patterns, and that gives you what you want. So there are, so I did this using two different circuits. So one circuit I call the target supervisor, and another circuit I call the critic supervisor. The idea of the target supervisor is that the supervising signal just tells you what the neuron is supposed to do, right? So the supervising signal is either a 1 or a 0. So you basically either have the supervising signal or you don't. If you have the supervising signal, that means that the neuron is supposed to fire. If you don't have a supervising signal, the neuron is not supposed to fire. Now, in order to implement this kind of supervisory circuit, you need to cheat a little bit. The reason why you need to cheat, I will say, is because of this situation here. So if the supervisor, right, the supervisor is 1, so the supervisor is telling you to fire, and also the neuron fires, so that's always going to be the case where you have the most calcium, right? Because you have calcium both from the supervisor and from the neuron. But we need, for the perceptron learning rule to work, we need this situation where both the supervisor and the supervisor fires and the neuron fires. We need there to be no change. So that means that if we use sort of the normal plasticity thresholds, this case will kind of always potentiate you. So in order to implement this, we have to cheat. Oops. I'm going to move my face a bit. All of our faces here. So we have to cheat a little bit by adding a third threshold for the calcium. So when you have very high calcium, then no plasticity happens, right? So that's the only way that you can get this fourth quadrant of the perceptron rule. Now, why am I allowed to cheat like this? Why am I allowed to add a third threshold where calcium doesn't happen? So it turns out that there's this paper by Tigray, sorry, I didn't put in the citation, where they did a bunch of these STD. This is Tigray. I don't think that was the first author. Yeah, so if you remember when Yuri Rodriguez presented his he had a very elaborate plasticity model. So it was based on these results from this Tigray paper. It's this 2016 paper. No, this one here. Yeah. So yeah. Oh, okay. Yeah. So effectively, what they did in this paper is they did STDP protocols. Hard to see here, but many different kinds of STDP protocols. So they do like two postsynaptic followed by one presynaptic. I think this is at 50 hertz. And effectively, what they showed is that this standard calcium-based plasticity model that we normally use, and this is also the one, basically the one that we're using, is not entirely correct. So they have one or a series of figures here where basically they show that if you're looking at as a function of calcium, they don't really have the calcium, but they have, let's say, they do calcium imaging and they look at that signal, so it's pretty close. So it sort of has this structure where it goes down again at very high levels of calcium. I'm not quite sure what these potency and response things are, but I use this plot as justification for the claim that when you have very high calcium levels, actually it's possible that you don't get plasticity anymore. Maybe it's true, maybe it's not true, but if it's true, maybe it's a feature and not a bug, because you can actually use this kind of curve in order to implement the perceptron. Now, if you don't want to cheat in this manner, what you can do is have a different kind of supervising signal, which we'll call a critic supervisor. So this is a supervisory circuit that tells you whether you were a false positive or false negative. So basically, if you were a false positive, it gives you a depressive signal. If you were a false negative, it gives you a potentiative signal. And if the neuron produced the right answer, it does nothing. So I don't claim exactly how this circuit works, but you can imagine that the brain can do this sort of thing, right? That it knows the answer, it knows what the right answer is, and it also sees what this neuron is doing. And then it compares them and it can tell you whether it was a false positive or false negative. And if you use this kind of circuit, then it's possible to implement the perceptron using the normal calcium thresholds. So in the first circuit, because there's only this potentiative supervisory signal, so you notice it's the same height each time, and it happens whenever there's a 1. Here with this critic supervisor, so there are 2 different supervisory signals of different strengths, so that's why you see the different sizes. And also, you know what, they stop eventually. The reason why they stop eventually is because eventually the neuron learns, right? And when the neuron learns to correctly respond to the patterns, it stops making mistakes, and so therefore the critic isn't criticizing anymore, right? So you're no longer getting inputs, and this is, again, it's a little bit hard to see here. It's very hard to see, but eventually what happens, I'm training this on 6 different patterns, so 3 patterns that are supposed to be positive, that it's supposed to spike for, 3 that it's supposed to not spike for. Initially, it makes mistakes. You can see it with the little X's here. You can also see it here. Whenever there's plasticity, that means that there was a mistake. And eventually it stops doing plasticity because eventually it gets all of the patterns correct. So you can do perceptron with calcium. You can also do homeostatic, this right signal, one-shot flip-flop, unsupervised learning of frequent patterns, or OJA's rule, different pre and post synaptic frequency dependent, Hebbian type rules. And this is all using the calcium control hypothesis with, you know, a little bit of cheating sometimes, but mostly not. So tuning, yeah. So bottom line is that calcium is all you need. And that's it. And it's 2.
Wait on time.
This is with Lee, yeah. Yeah. Okay.
אבל אם יש לכם אינפוט זה טוב, כי אנחנו רוצים לפעול.